that very interesting. I wanted to share, and I'll show you its power in the context of singularity resolution with two explicit geometric solutions. This will have some overlap with Raphael's talk. It's based on, it's a subset of these two papers that came out in October and an older paper. And the second part, I'll talk about some work in progress with these folks about a new set of questions we've begun to ask using the gravity path integral to make contact with Lorentzian subregions in gravity. So here I wanted to highlight Sami and Gwanda, who are grad students that have been, it's been a pleasure working with them. So I wanted to highlight that. Okay, so in GR we have theorems can be proved from a basic set of principles and assumptions. And there's evidence, there's been a lot of evidence by now that this structure extends in some sense to semiclassical gravity, and a sort of basic, perfect example of it is the semiclassical singularity theorems that Raphael already discussed in his talk. So I don't want to repeat it, but just to remind you of the structure of these kinds of theorems, some minimal assumptions about a spacetime is made, and we further assume that generalized entropy can be assigned to subregions. And we can formulate a theorem like this. If we have a partial Cauchy-slice sigma that's non-compact, and its boundary mu is compact, such that its generalized entropy decreases under deformation along this future horizon, then we can prove that there exists a singularity using a combination of some just topological arguments based on the space-time and some conditions on the dynamics of the generalized entropy, in this case the generalized second law. We conclude geodesic incompleteness. So that's the structure, and with this kind of structure a lot of other theorems can be proved. I don't want to go through this list. It's a whole bunch of things about quantum extremal surface prescriptions, their existence, their consistency with causality, etc. Not just minimal quantum extremal surfaces, all kinds of other quantum extremal surfaces. There's also, it's also modern singularity theorems, etc. So anyways, this is an amazing story of theorems and proofs, but it's old news. So the only thing that I want to emphasize here is just this, I want to explain to you a bit, some detail of this extended regime of validity. So just to, believe me that these theorems rely on these three basic things where they require a background spacetime, a definition of generalized entropy for subregions, and some constraint on the dynamics of generalized entropy. So what is the regime of validity? I mean, I think maybe the first go-to place is the perturbative quantum gravity regime, where we have the metric coupled to some, we have metric among some other number of fields, and we quantize the metric as usual, where the metric is an operator whose expectation value is given by some, in general, asymptotic expansion GH bar. I mean, I think the status of the framework is unclear here. There's some progress, but I don't have much to say about that. The other regime that's often considered is one where you consider a gravity theory with C number of matter species, and you take the following limit, where GH bar is sent to 0 and CGH bar is held fixed. So this is a very popular limit. I mean, these are some classic references of this. The desirable feature of it is that it sets to 0 the fluctuations of the quantum fluctuations of the background spacetime while allowing non-trivial back reaction. And that non-trivial back reaction is controlled by this species length scale that I've defined here. And that length scale is much larger than the species length scale. We have an expansion like this. But when you write a limit like that, you're basically committing yourself to a theory that makes sense at species scale, meaning that at least some observables are well defined at that scale. For example, the metric can be well defined at that scale, as an example. So this limit is brought up often, and at the very least, papers pay lip service to it. And this is so this CGH bar exactness of the framework is what I want to emphasize. But unfortunately, if you give me some general collection of C matter species, I don't know how to have control over computations at this scale. It's good to have a model where you have control over computations. And that model, a model like that is provided if the C number of matter species happen to come from a holographic quantum field theory. And in that limit, the theory that describes this limit are examples of these holographic brainboard models. So I'll just describe them a few, yeah, briefly. So this is a situation where, so this is a time slice of this scenario, where you should imagine the solid line here is where the semiclassical theory, which has a species scale, lives. And its partition function is defined through the bulk, through the holographic dual higher dimensional Einstein gravity bulk, in the usual way that a partition function of a CFT is defined, except some Neumann-like boundary condition is used, which sort of dynamically determines this metric on the brane. So there's a dynamical brane on which this theory lives. And when the length scales on the brane are much larger than the bulk ADS scale, an expansion like this emerges, where the brane theory is almost given by Einstein gravity, plus some higher curvature corrections, plus ... and these are suppressed by LADS squared. But if you use the usual holographic dictionary, remember that in the bulk, we're sending GD plus 1 to 0, the Newton's constant in the bulk, but we're holding LADS fixed. LADS is nothing to be scared of. We hold it fixed. And this translates in brane word language to a limit where you send the Newton's constant on the brane, this constant, to 0, while holding a species length scale fixed, because this combination of a certain central charge times the Newton's constant to this power is actually proportional to LADS. So these theories are under control at their species scale, because in the bulk, we're not scared of maintaining control of our theory at ADS scale. That's nothing to be scared of. Okay, so at length scales much larger than the species length scale, the metric on the brane can be expanded like this. But if you want the metric exactly, you can just solve for this location of the brane exactly. This is an equation that resums this series, if you want. And similarly, in these models, there's a definition of generalized entropy, where it's defined using an HRT type prescription with this higher dimensional extremal surface anchoring to a specific region of interest on the brane. So this is a formula. This is again a resummed formula in a sense of the species scale. This is a species exact formula for the generalized entropy. If you expand it in a limit where L is much larger than LS, then an expansion like we're used to emerges, where you have an area over 4G plus ... and it has infinitely many terms. So this, I've written it in a funny way where I factor out a C. So this now really looks like an expansion in LS. But this first term is just area over 4G. Anyway, so these are two important ingredients, which sort of, this is what I mean by having control over the theory at the species scale. And, this is things that are, for example, emphasized in this paper by Amparan, and these formulas are, at least I've seen them in these papers written very clearly. Okay, so these are two out of the 3 ingredients. And the third ingredient, which is the constraint of the dynamics of generalized entropy, can also be shown in these models. That's sort of the thing that the main dynamical ingredient in this axiomatic framework where all these conditions are proved. And I just sort of, this condition roughly says, called restricted quantum focusing, and it roughly says that if generalized entropy is locally decreasing or less than or equal to 0 under deformations along this null surface, then on a future slice that's sort of null deformed away from the first slice, this is maintained. So let me just put some caveats. This proof assumes the existence of this extremal surface. There's also a mild genericity assumption in this proof that I really am not worried about, but I just wanted to mention. I believe it can be relaxed. But with those caveats, this central assumption is proved, and the proof is also non-perturbative in the species scale. So it looks like we have all the ingredients to make this framework non-perturbative with the species length scale. Also, I should say that this condition can also be proved in an exact semiclassical limit of JT, but that's not as interesting as this exact semiclassical limit of the RS brane, because it's a little bit simpler, but it can be shown. And this was also so this follows very, very closely this work by these authors. We disagree on some definitions, but we somehow both agree on this conclusion. Yeah, and I also want to highlight that this paper has a whole bunch of stuff, but the JT section, I think the credit should almost entirely go to these collaborators that I've highlighted. Okay, so now that we have everything, okay, so this was just a formal argument that this structure should work non-perturbativity of the species scale. But let me just give you an application, because that will, just to communicate more viscerally what this buys you. So, going back to singularity theorem, so consider the Schwarzschild spacetime as your G naught. You can ask, can the singularity be resolved? And this, by definition, cannot happen in some perturbative quantum gravity expansion. So Raphael, for example, explained this in his talk. It's because basically singularities don't work well with perturbation theory. But if you have a species scale at which you have non-perturbative control over some new metric, then it becomes a non-trivial question whether the singularity is resolvable at the species scale or not. And the singularity theorem says that subject to some easy to verify condition that I discussed in the beginning, this can't happen. Okay, so now that it's a non-trivial question, let's ask it in, again, going back to some model where we have control over the species scale. So, here's a first example. Consider the BTZ solution. This is an Einstein gravity solution. So this is the analog of the Schwarzschild example, where instead of Schwarzschild, consider BTZ, which has a Lorentzian conical singularity at r equals 0. And you may, and if you have large number of species, these species, their stress energy tensor blows up at r equals 0 just by interacting with the conical singularity. And so we know that there has to be drastic modifications to things near there. So you could ask, could this generate a bounce scenario, for example? Could this change? Now it's a meaningful question to ask what happens. But but these easy to check conditions of a singularity theorem are satisfied. So the singularity theorem would suggest this is impossible. Now, non-trivially suggests it's impossible. And this is, so when you turn on species scale corrections, and this paper of Amparan and collaborators turned these species scale corrections in the context of a brain world model, and they find a species exact metric that sort of UV completes this picture at CG. And what they find is that indeed the singularity gets worse. If you look at this metric, there's an additional -1 over R term. And this could be viewed as like a singularity from the higher dimensional model that hits the brain. But on the brain, it has the interpretation of upholding the singularity theorem. Okay, but this was, species, it was 50-50, right? If it could have been resolved, or it could have been a bounce. So let me, to give you more argument to believe that the singularity theorem actually is working, let me give you an example where a singularity is resolved. So this is a double weak, so brain world models are simple in principle, but it's actually difficult to come up with solutions. So the only solution of this nature I found is a double weak rotation of another solution in another one of Amparan's papers. Let me just describe to you the solution. It's a Rindler wedge with a small Kaluza-Klein direction. But the state of the matter fields in the Rindler wedge are not at Rindler temperature 2 pi. They're at a slightly different temperature. So the stress energy tensor actually blows up on the horizon. So you're instructed to remove this from the locus of the solution, this red thing. So this is a geodesic incompleteness, basically, in this new locus. But again, because the stress tensor diverges, you would expect large corrections there. And now, because there's no trap surface in this region, or the conditions of the singularity theorem are not satisfied, it's allowed to be resolved. And when you do turn on a species effect, a species scale effects non-perturbatively, you actually do get that it's resolved. The way it's resolved is that the transverse direction sort of caps off, and it removes the interior. The region behind the Rindler wedge doesn't exist, and is instead replaced by a region that's very, very highly curved at the species length scale, but is not singular anymore. Okay. So let me just summarize this first half by saying I'm very amused by the fact that some structure in classical gravity wants to, in some sense, generalize beyond classical gravity in a way that's non-perturbative, at least in some scale. This is a bit mysterious to me. I mean, maybe you can tell me why this is not surprising or something. But one limitation of this whole thing was that we were sort of stuck in this brain world model. It would be good to have more examples of this happening. The only thing that comes to my mind, this is a speculative comment, is that string theory also has a power of species. And in some sense, the analog of this limit in string theory could be the limit where GH bar is sent to 0 and the string length is held fixed. And in the ADS quantum gravity setting, there is some recent technology developed to make contact with subregions in this limit. And it involves, I won't go through it, but you may wonder if part of the axiomatic framework can be extended to this regime. And one target you may have is to come up with a singularity theorem that's exact in the string length, but in this limit. That could, for example, distinguish between singularities that are allowed to be resolved by stringy corrections and ones that are not. Okay, next I'll go to the preliminary work on some complementary approach to making contact with subregions in gravity with the gravity path integral. Okay, and here I'm just going to work with classical gravity, so we're shifting gears. Is there a time tracker? Oh, it's on there. Oh, we're good. Okay. Okay, in a standard application of the gravity path integral, asymptotic boundary conditions on codimension 1 slices, like sigma, prepare a state on the boundary of sigma. Here I've shown a boundary of sigma that consists on this left and right pieces. And this state can correspond to a Lorentzian geometry. So this is an example where we are all familiar with, where this prepares an ADS-Schwarzschild black hole. The sense in which this corresponds to Lorentzian geometry is that it dominates the norm computed in this state. So this is half of this sigma, the data on sigma is half of the asymptotic boundary of Euclidean ADS-Schwarzschild. So in an attempt with my collaborators to make contact with Lorentzian subregions in gravity, more general Lorentzian subregions, we've been pursuing the following speculative idea. The idea is that some class of non-asymptotic boundary conditions in sigma also prepare a state on the boundary of sigma. So let me explain the wiggle rooms in this statement. So first, the boundary condition on sigma could be, for example, Dirichlet boundary condition or conformal boundary conditions or something else. But more importantly, there is a wiggle room in what I mean by some class of non-asymptotic boundary conditions. All I mean is that the metric on sigma, see in this example, the metric on sigma was constrained to be asymptotically ADS, and we're just removing that condition. And there are degrees to which you can remove this condition. And at this point, I guess at the level of preliminary work, we're not super committed to this, but we want to say some version of this is true. By the way, I want to say that this is not I don't know who to attribute this idea to, but let me just say some stuff in the past few years where this idea has appeared. In the context of asymptotically locally ADS, some statement like this was made in this paper, and some sort of axiomatic formulation of this. Oh, let me actually say what I exactly mean by this first. Sorry, what do I mean by a state is prepared by HAB? Let's say it's some codimension 1 metric on sigma. What I mean is that you can draw a representation of the state with this shape, okay? But what is that? How do I define a state space? The way I do it is that I define inner products by saying you can glue this boundary data HAB to another state prepared with a different HAB, where you glue, you do the appropriate CPT conjugation for the bra and the ket. And now that you glue them, so if HAB and if the HAB1 and HAB2 have the same boundary, they're gluable on their boundaries. And now you get a complete set of boundary conditions that the gravity path integral can fill in. And this can produce a number, and this will sort of define your state space. And you can also do other things, like you can, for example, trace out the left boundary, which corresponds to these gluings, and this will get you an operator on the right-hand side, on the right boundary. And this was, for example, there's some axiomatic formulation of this kind of structure for a case where sigma is forced to be asymptotically locally ADS was developed here. But I think in the more general case where you go away from it, ideas like that, I think the closest to the way we think about it probably appeared in these papers by Aaron Wall and collaborators. And this went under the name of Cauchy-slice holography, which is why I called this second half partial Cauchy-slice holography. So I think the status of to what extent this idea is true is a bit unclear. The thing you would worry about, as we heard from Luca's talk, is the positivity conditions that would define a Hilbert space. It is natural to think that maybe some local conditions on sigma near the boundaries would be needed to guarantee positivity. And also, I should say that in a provocative essay written by Aaron, in cases where this may lead to negativities in the Hilbert space, those were embraced as features of gravity as opposed to problems with this prescription. But so this is preliminary work. I'm just gonna assume some version of this works and share you the kind of calculations you can do with it, and just leave you with the applications we have in mind. I'm just, just that. So, okay, so what can you do with it? So in the previous, consider the Adias-Schwarzschild spacetime, and consider a state preparation which is done by this blue slice. So now my blue slice is directly inherited from the Lorentzian spacetime, and I view it as a state, preparing a state on the left and the right boundary. So the kind of thing that we learn to do with gravity patterning that teaches us important things has to do with computing, for example, entropies, holographic entropies. So how do we compute, for example, the entropy associated to the right-hand side using a state preparation like this? We can turn this into so gluing the left boundary, tracing out the left boundary and constructing a rho r operator in this framework would correspond to looking at this. So this is a sort of a representation of the rho of r as a boundary condition. And you can compute trace rho to the n. This can be turned into a complete set of boundary conditions that gravity should fill in. And we obtain replica saddles here. And the replica saddles look like this. This is a case of n equals 3. Where this is 1, this is 2, this is 3. And we obtain and this can be explicitly computed. It's not, this is a sort of in some sense, you could say a special case of the Lucas-Maldacena discussion. And one thing that may be interesting here is you may have thought that this state preparation is sort of the closest to a tensor network structure, where you have fixed the intrinsic metric. So that should match tensor network sort of answers for the entropy. But we actually don't obtain a flat Renyi spectrum. So this is, I'm not saying it's in contradiction with tensor networks. It's something that a couple of us have found amusing. So let's take it to the next level. We're interested in Lorentzian subregions at the end. So I should say that the Von-Neumann entropy at the end comes out to be the area of the bifurcation surface. So let me consider now a shorter slice. We want to eventually be free of ADS, basically. And this is sort of a first step toward doing that. So now you can view this partial Cauchy-slice as preparing a state on the union of these two boundaries. Again, this maps into a boundary value problem for trace rho to the n, and we get solutions like this. Oh, sorry, I'm realizing I did not explain the solution. This is basically what fills this in is a portion of a Euclidean Adias-Schwarzschild with some area an. So it's just this portion of it. So the dashed line is the full sort of Euclidean cigar, and the replica saddles associated to this are the interior part of it. And the interior part changes to this in a case where the slice gets a little bit shorter. But the Von-Neumann, so the Renyi spectrum changes, the Von-Neumann entropy remains the same and is given by this area. Next, you could take this all the way to the extremal surface. And in that case, what we obtain is this solution sort of collapses in on itself, and the Renyi spectrum becomes flat. But again, the Von-Neumann entropy comes out to be this. Now let's go past this and consider a slice that's sort of less than half. In this case, the boundary value problem for trace rho to the n is well defined, but we currently don't know what the solution is. I mean, this is just, again, because it's preliminary work, but you could imagine that just because we have lost this extremal surface, the answer should be more difficult to find. But again, with analogy with tensor networks, you might expect that the Von-Neumann entropy of the right-hand side in this state preparation would be given by the area of this inner boundary, but we have not confirmed that, and we just don't know what the answer would be in this case. But it's the problem is well defined. Okay, let me just say that we have so far not, I'm interested in making contact with Lorentzian subregions, but we have not really done that yet, because just specifying a codimension 1 metric does not specify a Lorentzian embedding. This can be shown with these with this example, consider two different area Schwarzschild spacetimes, G1 and G2. And you can take the same exact codimension 1 metric, HAB, and embed it. This is the same HAB embedded in two different geometries. So if I do this state preparation, I'm not in any way committing myself to this geometry versus that geometry, right? Okay, so, I mean, this is, yeah, so, you know, so currently our best way to, you know, so this is a little bit like saying, yeah, if you fix the position exactly, you don't know anything about the momentum. So we think that, you know, in the most natural way for the kind of questions we want to ask to make contact with a specific Lorentzian subregion is this procedure, which makes sense in real analytic spacetimes. So suppose these are real analytic spacetimes, then I can construct a, what is this called? Gaussian normal coordinates around this slice, and I can do a similar Gaussian normal coordinates around this other slice. And in a real analytic spacetime, by definition, this function HAB should be continuable to IT. And if I can deform these slices a little bit in the IT direction, obtain these pink slices. Now these pink slices are a little bit different between these two pictures. And in this, and it turns out to be the case that H tilde AB1 prepares this Lorentzian geometry in the sense that the sort of a contribution to the norm of the state prepared by the pink slice is given by geometry that has this Lorentzian section, and similarly for this. I mean, another way to say this is that the complexified metrics H tilde 1 and H tilde 2 are actually different now, so they can distinguish between these geometries. Okay, so the kind of computations we think we can do now with this is to consider a state preparation like this, which prepares the state on the union of left and right boundaries. And we think that if in the Lorentzian spacetime there exists an extremal surface in the domain of dependence of this partial Cauchy-slice blue in the Lorentzian section, then the Neumann entropy of the right-hand side will be given by the area of that extremal surface. This would be again, I guess this is. This would follow arguments very, very similar to Lucas Malacena, or the generalization of it in when you have Lorentzian, both Lorentzian and Euclidean parts to your geometry. Okay, but again, an interesting sort of question mark arises when you bring this right boundary into the black hole. So this is, I think, kind of the analog of this confusion. When you do this, the entropy of the right-hand side, the boundary value problem corresponding to computing Neumann entropies and Renyi entropies is well defined, but at this point we don't know the answer. Okay, so this was we were just sort of honing a framework to then ask questions with it. So let me just finish by telling you the kind of questions we have in mind to ask with this. So, okay, I think this question is particularly in my mind. I don't know if everyone else in the team likes this question. But, so there's been a lot of, so it seems like a sought after question is whether the area of the de Sitter horizon has an entropic interpretation, or what is the interpretation of it? To me, it sounds like within this framework, the most natural way to ask that question is to consider a state preparation that lives here. So consider this state preparation that it stops short of being a complete Cauchy-slice, so it will have still some boundaries on the left and the right. And using this state preparation, now you can ask, if you want, you could think of this remnants, stopping short of completing the Cauchy-slice as sort of introducing observers. That's maybe the way to say it. And with this state preparation, now you can ask what would be the Neumann entropy of the right-hand side or the left-hand side. This is like a new way of asking the question of sort of asking the question of whether the entropy associated to, let's say, this left region is given by this extremal surface. And to be honest, it seems extremely, we find it very not feasible at all that the answer would come out to be the area of the Sitter horizon. But this is under construction. I can maybe say more in the discussion why we don't think that. And let me just leave you with another goal we have with this construction, which is these interesting proposals by Busso-Pennington on generalized entanglement wedges. So the rough idea that these guys have is that, so we in ADS-CFT, we are at this point used to the statement that a boundary region, a boundary cut, which I've shown in green now, has an entanglement wedge, which is shown in this with this gray shaded region, and its entropy is computed by the area of the extremal surface. So these guys put out a provocative proposal that maybe this is there's something more general you can do, which is to input, instead of a boundary region, a bulk region. Here I've shown an example. And that this will also have a corresponding entanglement wedge, which is this gray region in this case, and its entropy in some sense, some fundamental entropy of this bulk region is computed by this extremal surface. And the story gets a little bit more interesting and complicated when the region goes into the interior in a way that maybe is commensurate with the way that our story got a bit non-trivial when regions went into the black hole interior. But I mean, this proposal is crazy, right? Come on, Jeff, admit it. Okay. But I think it's hard to dismiss because there is a lot of consistency conditions that it satisfies along the lines, like conditions like quantum information theoretic constraints, like the strong subadditivity that these entropies obey, etc. And I think I hope it was clear that the kind of questions we're asking with this partial Cauchy-slice holography framework should be directly related. Like if this proposal is correct, I would think it would be provable in some sense using this this framework, where you basically reduce questions about Phenomenon entropy of B into some sort of a holographic entropy calculation, which involves partial Cauchy slices as opposed to complete Cauchy slices. Yeah, so as I said, this is again work in progress, but I'll be curious to see if anyone has any opinions about it. So I'll just end here. Thanks.
Can you explain why in the Sitter case you don't expect to get the bifurcation surface for the entropy law?
Yeah. So one way to think about it is that, in the limit where the slice gets longer and longer and longer, you'll just lose the edge. You lose the edge of the. So the only reason we have a non-trivial Hilbert space in this case is because sigma has a boundary, the right and the left boundary. But as you make sigma bigger, in a limit where sigma becomes complete, you don't have a boundary anymore. And then it shouldn't make sense to have an entropy come out to be the entropy, to be the area of the extremal surface.
I hate to interject here, but
Yeah.
There's an answer to that. I know I was rushing in my talk on this point of the doubled system. First of all, there's absolutely a one-sided microstate count. It's not a question anymore. When it comes to the doubled system, in say a thermal field double-like setup, there's an analog of the Hawking-Page transition. If you only have the joined,
So sorry, this is the Dirichlet boundary condition on a whole. Okay.
the joined solution as the dominant solution, when those points you've drawn are quite close to the horizon, they Otherwise, you have what we call the pole patches dominating. It's a decoupled pair of pole patches that you're creating. So the thermal field double is only generating for you the connected solution above an analog of the Hawking-Page transition. So the argument you just gave about pulling the thing, making sigma larger and larger, does not apply for the dominant solution, which is connected. And given that, what I showed in the talk is that this question, which is very interesting, is UV sensitive. There's it is not trivial to declare that the cosmic brain wants to go to the boundary because that you're assuming something about these very high energy quantum field modes, for example, that back react. So I think it's a great question, but it's not a classical question. It's not a question that applies if you try to pull the points all the way.
Yeah, I was in your talk, and it's clear that there's probably some connection between these two, but to be honest, I don't exactly understand the connection, and maybe we should talk more. I mean, you have this sort of time-like Dirichlet boundaries here. This is a space-like boundary.
This Hawking-Page transition first, because it affects this response you were giving it about pulling the points to the pole. The connected solution may not dominate.
So it's a completely different framework, Eva.
Sorry?
It's not related.
Yeah, I mean, I don't see exactly the connection. I mean, sorry, your claim is that if in the region, in the limit where this blue thing becomes very, very small, we should get that the answer is given by the area of the Sitter horizon, but not when the region is big.
You'll find that the dominant saddle is a disconnected set of pole patches instead of the connected thing you've drawn. You said you were possibly talking about a Dirichlet boundary condition and a thermal field double kind of construction. So I don't. This
is the Dirichlet that I'm discussing. Hold the metric on this time symmetric slice fix.
Okay, but you have some boundary condition on your L and your R.
Yeah.
Right? Well,
the boundary condition is specified just on the entire blue slice, not on L and R.
Well, you have both, I think. You must be saying something about the boundary condition at L and R as well.
Well, the boundary is, I guess, the only thing I would like to specify is a 3 metric or a codimension 1 metric on this blue slice. And because I'm not interested in evolving this to the future and past, this is like a state preparation at the moment in time, if you want. I don't have to tell you like how I'm evolving the state to the future and past on L and R. So in that sense, I don't have an additional boundary condition, but I do have a sort of an initial state, just a codimension 1 metric boundary condition. Sorry. Yeah.
About boundary conditions, or if you're doing a replica trip for this blue region, or do you automatically get some flat spectrum because there's no like conical excess? Like you don't have to. Is it a flat spectrum?
In this case, yeah. I wouldn't.
There's no anchor to the boundary. I mean, because what's enforcing the conical excess in the case of trace row to the n?
Well, I don't know if there will be a conical excess.
Well, I'm asking. That depends on what you're doing.
No. I mean, in principle, you have to set up the boundary value problem and not allow any deficit angles, okay. Right?
To make my question more precise, is there a difference between the path integral that you would set up for rho and rho squared?
Oh yeah. I mean, the difference is, well, sorry, if I were to draw it here, this is what rho is. So its trace would be gluing these two and letting gravity fill it in. The rho squared would be this, where you glue them. And this is computing trace rho squared. Now gravity fills this in. So it's a different boundary condition. In some sense, trace rho squared is a doubled boundary condition.
Oh, this is just for the right region. This is
Yes. This is trace rho r. Yeah, that's what well, that's why I was, this is one way you can define entropy in some static patch. This may be this was a kind of a speculative application where if you want to somehow in this framework compute an entropy associated to one side, this is what you would do. You introduce two boundaries and then trace out.
an entropy associated to the full blue region.
No, I think no. I don't know how to say that. Yeah.
Last question.
Yeah. In the ADS case, are all the saddles that you found just pieces of the Lagrange multi-center saddle that you cut out? Or
They are pieces of Schwarzschild geometries, Euclidean Schwarzschild geometries, but so let me just to be clear. So I don't exactly know what you mean by Lucas Malacena geometries, but this state preparation, if you want, you can apply Lucas Malacena to, and it results in a certain Renyi spectrum. The Renyi spectrum associated to this state preparation is different from the Renyi spectrum associated to this state preparation. So, the solutions, the ANs, if you want, the area of the fixed point is different. But they are nevertheless all, because of just the too much symmetry that exists here, these are all Schwarzschild geometries. Nevertheless, they all have the same Phenomenon entropy, though. The Phenomenon entropies are all the area of the sort of parent geometry.
Just to clarify, I guess the ADS case is general, but if you were to run this argument, this construction for a general, the choices of four-dimensional geometry, would you expect that to get so for a general spacetime, would you expect that the saddles that you get would still be pieces of the?
Oh, no. What? Okay. Maybe we should discuss that because I don't exactly know what you mean by pieces of the Lucas Malacena geometry, maybe in that sense. Sorry? Yeah, the spirit, yeah. So, all I meant by that is that the boundary condition associated to this rho of R, when you put n of them together, the boundary condition is Zn symmetric. And the idea in Lucas Malacena was to sort of hope or posit that the dominant gravity solution would maintain that Zn symmetry. So that's all I meant to communicate with that reference. Not that these are literally some, Lucas, I guess, that's all I meant to emphasize.
Okay, let's thank
Okay.
everybody again.